With this next lesson, we are going to look at electron configuration. So we really have to pay attention to the idea that electrons, even though they are in shells, and we can look on the periodic table and say, hey, if I'm in row 3, then I have 3 shells. We have to understand that there are things called subshells. Okay, so electrons, even though they're in shells, like we're saying, hey, we're here in a school building, there are different floors within our school building. Okay. So we're going to talk about S, P, D, and F subshells, and then you'll probably hear me say multiple times, follow the yellow brick road. Okay. So the learning goals we have here, we're going to describe the structure of an atom in terms of electron shells and subshells. Okay. We're going to use the periodic table to determine the electron arrangement in an atom and write electron configurations. We'll be able to explain the organization of the periodic table in terms of the arrangements of electrons and subshells. And one great thing that we'll do with this lesson, which I think makes it way easier to understand, we're going to play a game, and we're going to pretend that these subshells are rooms in a hotel. And every year I have pretty good success with my students in getting them to understand how we fill the electrons and the orbitals in there. Okay, one key vocabulary term that we have here is electron configuration. Okay, this is basically a notation for keeping track of where the electrons in an atom are distributed among the shells and subshells in an atom. Okay, so you will see coefficients essentially. So you'll see big numbers, you'll see letters, and you will see superscripts, or we also like to call those exponents. Okay, where we see the large numbers or coefficients, that is going to tell us our shell number. Okay, so this is shell 1, shell 2, shell 3. Okay, the S's, P's, D's, and F's that we'll see will tell us subshells. And then the numbers tell us number of electrons in the subshell. Okay, so we'll see 3 different things that we have to pay attention to on here. Okay, all right, so take a look here. These drawings show 2 different ways to represent the arrangement of the electrons in the atoms of the element calcium. Okay, well, what are 2 differences that you see? Okay, well, 2 differences, I can say that the one on the right hand side has way more circles represented out here. And another difference would be that the electrons on the one that's on the right-hand side aren't all on the same exact circle. Okay, 2 similarities, they have the same number of electrons. Okay, they also show us that the electrons are arranged outside of the nucleus at different distances. Okay, so let's talk about electron configurations. Okay, the periodic table is super important for this lesson. We're going to determine the arrangements of the electrons into those subshells. Okay, so you'll see here the nucleus will always be represented when we have these drawings. Okay, the very first shell will have a total of 1 subshells. Okay, shell 2, or if you look row 2 on the periodic table, will have a maximum of 2 subshells. Shell 3 will have a maximum of 3 subshells. For the most part, that's as far as we will get, row 3 or the 3rd shell. But sometimes we will get a little bit further. But you have to understand that those shells can be broken up into smaller subshells. Okay. So take a look here. Shell 1, so N represents the shell number. It can hold a maximum of 2 electrons. Okay, it has 1 subshell, and that subshell can hold a maximum of 2 electrons. Okay, if we look at row 2 or shell 2, it can hold a maximum of so again, in that second shell, we can hold a maximum of 8 electrons, and there are 2 subshells in that second shell, and the first can hold 2 electrons, the second can hold 6 electrons. Okay, in shell 3, we can hold a maximum of 3, or we have a maximum of 3 subshells, and that third shell itself can hold 18 electrons. The very first subshell can hold 2 electrons. The second subshell can hold 6. The third subshell can hold 10. So 2 plus 6 plus 10 gives me 18 total electrons, okay? In row 4, so we're looking potassium all the way over to krypton, we can hold a maximum of 32 electrons there, okay? You will see that the shell number is represented here, so 4, and then we have 4 subshells here, S, P, D, and F. The S subshell can hold 2 electrons, that P subshell can hold 6, the D can hold 10, and the F can hold 14. Well, let's take a look at our similarities here. Here is an S subshell, here is an S subshell, here is an S subshell, and here is an F subshell. Take a look. Every S can hold 2 electrons. Okay, let's look at the P's. Okay, every P can hold 6 electrons. Okay, every D can hold 10 electrons, and then every F, I'll make that look like a cloud, every F can hold 14 electrons. Okay. Okay. Okay, in an electron configuration, the number indicates the shell number. The letter indicates the subshell, so just like we talked about when we did the definition. And the superscript or that exponent tells us the number of electrons in that subshell. Okay, same picture that you saw in the beginning. Okay, here's an example of sulfur. Sulfur has an atomic number of 16, so we're going to say that it has 16 electrons, okay? And this is the electron configuration for sulfur, okay? Notice sulfur is in which row of the periodic table? Well, sulfur is in row 3, okay? So row 3. So that means it has 3 shells, okay? 3 shells. Do you notice here's shell 1, shell 2, and shell 3, okay? We're representing 3 shells. Now, we cannot fill a higher shell without, or put electrons in a higher shell without completely filling a lower one. Okay. Let me go back to this. There is a little path that we'll follow. This is something great to write down in your notes here. You want a column of S's, a column of P's, a column of D's, a column of F's. And make sure you line up any 1 with a 1, a 2 with a 2, the 3s with the 3s, so on and so forth, okay? And I will refer to this in class as follow the yellow brick road. We will move at an angle, and we'll put this on the back of our periodic table if I didn't already do so for you, to follow through there and make sure that we are going along the correct path, okay? The directional arrows that you see here, this is how we fill these subshells, okay? Well, where are those S's, P's, D's, and F's coming from? Anything that is a subshell with an S, you will see it represented here, as well as over here with helium. Any of the P's, you will see here. D's in the middle, and your F's will be down in your lanthanides and actinides. So let's do this. Let's pay attention. We know S's can hold 2. Any S subshell can hold 2 electrons. We'll take a look. Here is the 1s subshell. It goes from hydrogen to helium. How many electrons are there between hydrogen and helium? 2, okay? Let's look here at the 2p. We know every p subshell can hold 6 electrons. How many blocks do you see here on the periodic table? 1, 2, 3, 4, 5, 6. Makes sense? D's can hold a maximum of 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the F's can hold 14. So there should be 14 blocks going across there. Okay. And if you refer to this picture, we actually fill in this order. So if we say we are looking for phosphorus, okay, phosphorus, which phosphorus is found here in group 15. Okay, and phosphorus would be this block right here. Okay, and we have 15 total electrons. Well, how do we fill this in? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, we would go up to the 3p subshell with our electrons. Okay. It might not make a lot of sense as we do this here, but when we do the hotel activity, I promise you this will make a lot more sense. Okay. Those subshell blocks don't always go in the numerical order. So we do 1s, 2s, 2p, 3s, 3p, 4s, and 3d. Notice we go from a third shell to a fourth shell back to a third shell. Okay. Elements in the different subshells blocks have related properties. S blocks contain all reactive metals. D blocks are our transition metals. P blocks form white compounds. Okay, again, so this is our follow the yellow brick road. So we start out filling the 1s. We then go down to the 2s. Once we get all the way to the left and there's nowhere to go, we start back at the end. So it's like a ray when you're in math class. We go from the tail to the tip. Tail to the tip, tail to the tip. Okay. There's a shorthand way to write electron configurations, and we can do that with, putting the noble gas in parentheses and starting our electron configuration as to whatever comes after that noble gas. And it's always going to be some S subshell that comes after a noble gas. Okay. And that noble gas shorthand will give us really great information about the number of valence electrons in an atom, but make sure you do pay attention to what shell you're looking at, okay? If I show you this is a handwritten out electron configuration. So we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. Well, let's figure out how many electrons we have in order to decide what element we have. So from here to here, we have 10 electrons, right? From here to here, we have 10 electrons, okay? And then we have 6 more, okay? So we have an atomic number of 26, okay? Atomic number 26, which gives us iron, okay? So this tells us I'm showing iron. Well, let's look on our periodic table, okay? What noble gas comes before iron? So iron is in row 4. If you go backwards, you will see that argon is the noble gas that comes before iron, okay? And if you put your noble gas shorthand here, and we start with the S subshell that follows the noble gas, you have to think, okay, argon has an atomic number of 18 and iron has an atomic number of 26. So this means I have to represent 8 more electrons after my noble gas shorthand, okay? Well, how does this work? Okay, since iron is in row 4, I'm in shell 4. Okay, so what comes after 4s, and you can go back and look at that follow the yellow brick road path, that would be your 3d subshell. Okay, so you would put 6 electrons in that 3d subshell. Again, practice will make this make so much more sense. Okay. Noble gas shorthand also tells us the number of valence electrons and how it changes from one element to another element across a period. Okay, take a look. Look at the third row. Sodium, the noble gas shorthand is Ne, and we have 1 electron in the 3s. Okay, magnesium, noble gas shorthand starts with Ne. And if you're wondering, hey, all of these have a noble gas shorthand of Ne, fantastic, because neon is the noble gas that comes at the end of row 2. So before we start row 3, that would be the one that we're going to start with, okay? So we would have 1 valence electron, 2 valence electrons, 3 valence electrons, 4 valence electrons, 5 valence electrons, 6 valence electrons, 7 valence electrons, 8 valence electrons, okay? But something to pay attention to. You can only do valence electrons in the same shell. Okay, notice shell 3, shell 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. These are all shell 3. If we would magically throw a 4 in there somewhere, this would be the shell that we're looking at our valence electrons in, okay? Remember, your valence electrons are in your outermost shell. So if we have a bunch of 3s and then we have a shell 4 or some subshell for 4 listed in there, we would have to, go with whatever the number of electrons would be in there. Okay, you can easily identify an element from its shorthand configuration. The ending of the noble gas shorthand will show you where on the periodic table that would be. Okay, the last subshell term indicates what block it's in. The number in front of the letter tells us which subshell or which row it's in. And the superscript tells you how many electrons are in that specific shell, so you can count over and under and around and through. So here are just some really easy ones that you'll see. Okay, we're going to talk about some different laws, some different principles with filling subshells. The Afbau Principle, it's also called the Afbau Rule. It states that in the ground state of an atom or an ion, electrons fill atomic orbitals of the lowest available energy levels before filling higher levels. So we will fill a lower energy level before we fill a higher energy level, okay? Lower energy level before we fill a higher energy level. Hund's rule says that every orbital in a subshell is occupied by one electron before we fill an orbital with another electron, okay? All of the electrons have the same spin or they're facing the same way. Pauli's exclusion principle says that that 2 or more identical electrons with the same spin can't, be found in the same block. Okay, electrons are unable to have the same spin in the same subshell. So if we take a look to the right here in this picture, look at A, you see up, down, up, down, up, down. Okay, this right here, this first example doesn't work because according to our very first rule, you can only have one electron in each block before you give them a roommate, okay, or before you give them another, okay. B here, that does work, okay, because you see up, down, up. We have 3 total electrons. We don't have anything matched up here. Letter C, the problem that we have here, we should have an up and a down. Those spins or the arrows shouldn't point the same direction, okay? If you look here, letter D, we're representing 7 total electrons, okay? The only problem that we see here, again, is the spin. We should have an up and a down, not an up and an up, okay? So this should be up, down, and then you see each of these have their own orbital or their own space before we are moving on to double them up, okay? So what we're going to do with the Hog Hilton game, some things that you'll need. You will need your periodic table, your polyatomic sheet, your notes from this lesson. I'm going to give you pigs that you have to cut out, and I'm going to also give you a hotel sheet, okay? The rules, you want to write those down in your notes here. We're going to practice them, and then we're going to answer some questions on them, okay? So the rules. Hogs are lazy. Hogs can't stand each other, but there is an exception to this rule, okay? They can't stand each other, but if they're lazy enough, they'll be around each other, okay? If hogs end up in the same room as each other, they will face opposite directions because they can't stand each other, okay? And they stink, so you can't put more than 2 hogs in each room. Well, what does this mean? Hogs are lazy, okay? If hogs are lazy, we want to fill lower energy levels first, okay? We want to fill lower energy levels first. So that means with this Hog Hilton game, we want to fill lower hotel floors first, okay? The hogs can't stand each other. So that means they don't want roommates. Okay. They don't want roommates, but if there is an open bed, so pretend that this hotel has 2 beds in every room, okay? If they have a choice of taking a roommate on the first floor or climbing up the steps to get to the second floor, they will then take a roommate, okay? If hogs are in the same room, they'll face opposite directions. Okay, if they face opposite directions, one pig will face up, the other pig will face down. They don't want to look at each other. They can't stand each other. Okay. The hogs stink, so you can't put more than 2 hogs in each room. So each room is similar to an orbital. Okay. No more than 2 electrons in an orbital, no more than 2 hogs in each hotel room. Okay. Your hotel will look similar to this. I'll give you a large one that you can move around. Okay.